forward. So anything that we've already gone through, effectively, that's why it's going to be highlighted. So that means it's going to be on a previous lecture video. So we can go ahead and talk through any questions you guys had. What the goal was, you're going to try to come up with some questions you guys wanted us to work on in class. Make sure I get all my happy little things up so I can see who's sending me questions. You can obviously unmute and ask anything you guys want, or just let me know what number you want to go ahead and work on. Okay, so for 29, so it's not really whether it's seated, it's more of just our physical positioning. So we want to be in a neutral spine position. Most dangerous position to be in rotation is a flexed position. So that is definitely going to be a flexed position. If we go to number 10. Okay, so remember, when we're talking about force production, we've got the contractile component. So that's the part that is created by the sarcomeres. Then we've got the parallel elastic component. That's effectively the stretch part that you're getting from the muscle itself. Now, the tendon is going to be the series elastic component. Because remember, it's going to stretch a little bit and it serves as a dampener of the force that we're producing so we don't accidentally tear a muscle off. Dakota, your mic is unmuted. If you've got a question, go. Okay. What other questions you guys want me to go ahead and work through? Right. Okay, so how do we increase stability? Well, we can widen the base, lower the center of gravity, shift our center of mass towards the oncoming force, What else can we do, guys? Yeah, it's going to be cortical and trabecular, but we'll get there in a moment. Increase our mass. What else can we do, guys? We can just center our center of gravity. Okay, so this is going to be cortical bone. Whereas trabecular, no worries, we'll go through Bicep. Okay, so 54, notice we've got our list here. So for hip flexion, it's gonna be lifting our knee up. Our iliacus, our psoas, our pectineus, rectus femoris, sartorius, and tensor fasciae latae, TFL. Now the real major ones here is gonna be your TFL, your rectus femoris, and then your iliopsoas. Hip extension, so obviously pushing that leg behind us. That's gonna be our glute max, semisinus and semimembranous, and then the long head of the bicep femoris. Adduction, pulling those legs together, are 3 different types of adductors, so adductor magnus, adductor longus, adductor brevis, and our gracilis. And then hip abduction, so pushing those knees out, glute med and glute minimus. Internal rotation is gonna be glute minimus, and then external rotation, we're talking about piriformis, superior and inferior gemellus, and the quadratus femoris. Okay. So remember, as that ball is spinning through the air, so if it's got laces while it's doing so, then effectively the laces, if we're throwing a curveball in baseball, we're pushing the air down on one side and up on the other. So what we're doing is we're creating a little bit of a vacuum underneath it. So that in turn is effectively, we're creating a higher pressure on the left side and the top of the ball and a lower on the bottom and the right. So when a left-handed person throws a curveball, it's going to actually break down and in. Now, remember, knee valgus is essentially going to cause your knees to naturally buckle in, just kind of the way that your bones are built, which can obviously lead to some knee issues. And then you need to lay down or hang from a bar. So any questions you guys would like me to go ahead and go through? So really I'm just kind of rattling off answers because I'm not seeing anything, but I might be going a little too fast, and that's okay. Go for it. For most folks, you're going to find that you're probably going to need to write at least 4 to 5 pages. Mind you, you'll have tables in there when you're going through what muscles are doing what functions. And then, this is the degrees of motion they change. This is the velocity, acceleration, torque, and force. Otherwise, yeah, your maximum, there really isn't one. If it's taking you 10 pages to do it, then I think you're punishing both of us with it at that point. So I'd say probably between, like I said, at minimum, that's gonna be 4 dense pages, full pages, not including a title page or something else you guys might do. Then yeah. Yes, it's the tables are going to look relatively similar to how you're doing those assignments. That's why I wanted you guys to kind of get some practice doing it there. It's 22 and 27. Okay, what is the angular momentum of an object that is spinning at 10 degrees per second with a radius of 1 meter and weighs 10 kilograms? Okay, so remember our angular momentum is going to be equal to so it's H equals, excuse me, the mass times our radius squared times the rotational velocity. It's a lowercase omega, but I don't know how to get to that really quickly through here. So H is going to equal, well, the mass, which is 10 kilograms, times 1 squared times 10 degrees per second. Now, in a perfect world, you do that in radians. I'm letting you guys obviously do that in degrees of radians, just whichever makes it easier for you. So then that means, well, 1 squared is still 1. 10 times 10 is 100. Okay. So then if we go to 27. Okay. Lifting force a bicep has to produce, so it's the bicep itself. If it has an attachment angle of 45 degrees and is holding a weight that is 10 centimeters from the elbow that weighs 10 kilograms, the arm's center of mass is at 5 centimeters and weighs 5 kilograms, along with the attachment of the bicep is 1 centimeter from the elbow. Okay, so this is where we have a force times force arm equals resistance times resistance arm. So bicep force, we got no idea what that is, but we do know the bicep attachment is, and we can put in 1 because it's gonna be 1 centimeter. If you wanted to convert into meters, since we're gonna do both sides in centimeters, we can just avoid it, but that would be the other way if you want to have it written in meters. So, okay, you know what, screw it, I'm not gonna be lazy. Equals, now we've got 2 different ones to sum here, okay? So we've got a 10 kg weight, which we then have to multiply by 9.8 meters per second squared, okay? And then we're going to multiply that value by the resistance arm, which is going to be that 10 centimeters, so it's going to be 0.1 meters. And we are going to plus the weight of the forearm and its center of mass, which is going to be 5 kgs times, again, that 9.81, and which is going to then be multiplied by 5 centimeters, so it's 0.05, close parentheses. Okay. So from here, we're going to have force times 0.01 meters equals, and that's where we can pull our handy dandy calculator over, and we can figure out that 10 times 9.81 times 0.1. Okay, so there you go. We've got 9.81, and then we're going to have 5 times 9.81 times 0.05. So now we have 12.265. So then we're going to divide both sides by 0.01. So now we're going to take that value, divide by 0.01. We've got 1,226.25. Those are going to be newtons. But now we got to figure out the bicep force. So the sine of 45 degrees equals opposite over the hypotenuse. So our opposite is that 126.25 divided by our hypotenuse. So we're going to then factor it to hypotenuse, which is the bicep force itself is going to be equal to 1226.25 divided by the sine of 45 degrees. So that means our bicep force equals, take that, well, right now the easiest thing to do is just write in 45. Then we're going to go to our trig, sine. So we get this happy number, okay? So now we get to, what's nice thing about this calculator is it lets us know, so 1,226.25 divided by 0.707. Now I'm throwing extra values because it just entertains me. So 1734.17 or 18. And notice the answer in newtons, so we got to make sure we do our right calculations. What other questions would you guys like to work your way through? Okay, let's do it. Is this what you came up with, Marlana? Okay. Let me know if you have a question about any of these answers, though, Marlana. And then Taylor, can you unmute yourself?
Yeah.
Okay. So what do you mean by that? The language there is a little hard to understand.
Well, I was just doing the extra credit thing,
Mm-hmm.
and I can't remember if I was looking at velocity or force, but I was trying to figure out, like, from her falling, like, would the acceleration or the velocity have to deal with, like, the fall too, or just like her weight times 9.81?
Okay. So this work can kind of get a little complicated. So if we think about it essentially as simply as we can, okay? Like me sitting here right now, I have that 9.81 meters per second pulling me down. That's going to be occurring whether or not I'm standing or anything else. Now, as I stand up, I'm creating my own positive acceleration. So I have to produce not just the same amount of force as how much I get from the gravity, but the extra force that I'm producing above it in order to lift myself upwards. So arguably, I'm feeling a greater amount of acceleration than I typically do. Now, when you have somebody falling through the air, they have the effects of acceleration for the entirety of the time that they're falling. The key is their velocity is increasing until, well, thanks to the drag equation, well, just drag in general, they're going to hit that terminal velocity. So that's literally the fastest they can fall towards the earth. Now, what's going to occur is whenever they actually hit the object in the end, well, however long it took their body to stop, that is going to be the period of time they went from that peak velocity to a final velocity of 0, which that is the acceleration they feel, which is going to be way bigger than 9.81. Does that make sense to you?
Yeah, I think so.
Okay. What other questions would you guys like to work on? All right. Number 9. Okay, so remember, as the angles increase, so does the ability to absorb force, because effectively we've got wider rigging as we go over. And I'll go over that in just a moment as well. So smallest angles are in the cervical spine, and the largest is in the lumbar. So tibial torsion is where instead of the tibia being a straight line and the foot goes forward from the knee, it's going to be a rotation of one direction or the other. So the tibia is actually twisted. And this is just kind of one of those things that happens during development, not all the time, but on occasion, because there's natural variability in effectively the bone structure of humans. And effectively from that information, you can kind of see, okay, how's that twisting is going to cause the foot to naturally bow to go outwards or inwards, which now we're talking about a little asymmetry of how force is being produced and absorbed through the lower extremity. So those individuals typically can have greater issues with really just kind of the impacts from doing a lot of, especially if they're trying to do something that has very little variability in motion, like long distance running. No worries, give me one moment. That's insane. Yeah, yeah, I definitely would say that as well. Wow. Hmm. All right, Jordan, are you good? Okay, thank you. All right, so question that I pose to you guys. What is the force velocity curve and why do we care about it? So I want you guys, and we'll put you guys in, I'll probably just break you guys up into 3 groups. We're gonna give you guys, it's 10:01 now, let's give you guys 8 or 9 minutes to really talk about what the force velocity curve is, why we care about it, and how we'll apply it when we're working with athletics or we're working with anybody. Does that make sense, guys? So what is the force velocity curve and why we care about it and how we'd apply it? So it's 10:02 right now. Plan on coming back at 10:10 and being ready to post in the chat what you guys come up with. See you guys in a few minutes. answers in the chat. We'll see what you guys came up with. And Josh, you're unmuted, bud. Okay, Gabby, that's good, but you're not going to get a reduction in your peak velocity. The key is you're not going to necessarily get much greater forces being produced at those peak velocities. So we're shifting the curve up on only one side. Okay, and Chris, that's not bad, but you guys are flipping it. The key is when something's really light, we can't produce that much force into it because we don't have enough time to produce all that force into it. So when something's really heavy, we can produce maximal force because it turns out it's not getting away from us too quickly. Yeah. Yeah, not bad. And then it's okay, guys. We're living in the wonderful Zoom world, so we have to play around with some different buttons. So the force velocity curve is just that relationship between how much force we're producing and the speed at which we're moving. So when something is effectively bolted in place, like you can't move it, you'll be able to produce maximal force because it can't get away. But if I give you a broomstick and I tell you to lift that thing as hard as you can, well, it's so light, you don't have a whole lot of time to produce that force into it. And so hence your velocity is fast, but the force that you used is relatively low. And so we do plyometric training, power training in order to move the velocity side up. And we do obviously resistance training, strength training in order to go ahead and move the force component up. And we move both those up, we shift the curve in general, and that in turn is going to typically make somebody a better athlete. So, good job, guys. You guys ready for another little question to have you guys working together? Yes, maybe, no, not really. All right. So the next one is a bit of a doozy, okay? Because there's a lot going on here. So how does that bone mineral density change with time? Does it do so specifically? Okay. What causes this to happen? And then what do you do nutritionally to get this to occur? So think about the vitamins and minerals. Notice the pluralization that you're going to need in order to improve this bone mineral density. So how does that work? Specifically, think about, well, let's give you guys more context. So I threw that up in the chat for all of you guys as well. So it is 10:15. We'll split on 10:25. Okay, take your time, work your way through it, and we will go ahead and talk through your guys' answers. So the rooms are open. So whenever you're ready, go ahead and head on over in there. Jordan, you having issues, bud?
What'd you say?
Oh, you having issues getting into your group?
No.
So that, like anything else, we're applying enough stress to our bone structure in an intelligent way to maintain our bone mineral density and potentially even increase it. Because like anything else, it depends on what we're looking for. Austin, Jordan, Taylor, and Zach's group, do you guys have anything you guys would like to add? But yeah, I think Chris's group really hit this one out of the park. You know, in theory, if you can maintain the same level of physical activity, the bone mass really doesn't go down until we start to hit, yeah, the hormonal components, and that's going to be a bigger issue. That's all good, guys. It's all good. Just like being in a bad meeting, just because you can talk doesn't mean you should, because then it can last even longer. So yeah, we've pretty much gone through everything on the study guide. I got a couple other prompts that we're going to work through in class. But otherwise, I was thinking about letting you guys out a bit early today, if you guys are okay with that. And then obviously when we come back on Thursday, we're just going to be doing some more reviewing, and then we can really try to make sure that you guys are getting everything ready for your projects. With that being said, is everybody who's in here right now, have you and your group been able to make and take those videos of your amateur and your expert to the front, to the side, and overhead yet, or do you guys still need to do that? Awesome. Good. Anna, what's your group? Oh, okay, cool. Good, good. Right. So, yeah, we might next week just have you guys spend that Tuesday effectively working on your projects, hopefully, instead of class time. I'll still probably open up the Zoom, and if you guys have questions specifically on your projects, we'll work on it then. But otherwise, yeah, good work today. Remember, guys, when we're doing movements, and specifically those movement breakdown assignments you guys have, when a muscle is actively shortening, that's concentric. When it's holding its position while contracting, that's isometric. And when it's lengthening while fighting a resistance, that is eccentric. So whenever I sit down to squat, I'm eccentrically contracting my quads, glutes, hamstrings to a lesser extent. Then whenever I stand up, I am concentrically contracting those same muscles. So keep in mind, eccentric is the lowering, isometric is the holding the position, and then obviously concentric is going to be the lifting. So take care of yourselves, guys. Stay safe out there. And I will see you guys on Thursday morning when we will meet up and obviously go through a little bit more reviewing. So there's no other questions. Otherwise, you guys have yourselves a great day, and I will see you guys then. Sound good? For lower body exercise, we use some movement that involves some upper body movement, but just ignore it. Yeah, go for it. Yeah, I was thinking just keep it simple on yourself and do something like a squat, a lunge, a jump, etc. But yeah, if you want to do something that's a little bit more total, go for it. Now, obviously, you do have a total body exercise that's going to be the final assignment. So when you do that, that would be making sure you use a different movement than that one. So keep that in mind as well. So stay safe out there, guys, and I will see you guys on Thursday. So, all right, guys, bye-bye.